I think we're live. Double check.
I'm checking right now.
Oh, actually, one second. Let me. Again.
We're we're
All right. Yeah, one second. Because last time when I had VPN, okay, I think we're good. Make sure the internet. All right. I think we're good, right?
Yep, I think
Uh,
so.
All right. Hello, everyone. Welcome to today's episode of Corecast. I am your host, Tim.
I'm Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Corecast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to them. And then last bit of thing is we're currently working on shorts. So if you all have any suggestions for shorts, you want to see a 1 minute 1 minute soundbite on, let us know in the chat as well, and we'll take that into consideration. All right. So without further ado, let's get to it. So Tim and Mikey, this is an interesting problem, or interesting thing in the universe where there is clearly more matter than antimatter. In fact, I don't even see antimatter like anywhere I go. I mean, I've heard it's created in a lab and stuff, and there seems to be like universe seems to only be matter. So, I guess this leads to asymmetry. So I guess maybe can we give the audience maybe set some like groundwork stage of this like asymmetry problem and kind of where we're going with this in this discussion. So I'll point it over to you, Tim.
Yeah. So one of the things people realize, I think it started with with Dirac, and historically with his equations on I think he was trying to understand the governing equations for electrons, and he realized that in order for the mathematics to be consistent, you need an extra term, and this extra term ends up being sort of like it sort of had the same behavior as the electron, but just a tad different, just a little bit different. And eventually, we realized that this uh, proves sort of the existence of what we call antiparticles. So it's the postulate that every particle, um, in principle, could come with an sort of like an opposite pair. And for example, electrons could come with like an anti-electron, which has opposite charge, and many properties are equal but opposite, except I guess mass. That's the same mass. So things like electrons, protons, and neutrons, or the constituents the constituents that they're made up of, like quarks and gluons, they have antiparticles. Although some of them are special, like particles of light, where the antiparticle is itself. It is its own antiparticle. So, but then there's this concept of antiparticle that exists in the standard model of particle physics. And the thing is, if you convert all the particles to antiparticles, the equation actually doesn't change too much for the most part. And then therefore a question kind of arises: if the equations don't change very much when you switch from particles to antiparticles, how come the world sort of have a bit of a favoritism? It favors particles over antiparticles. At least, this is what we see in our universe. So there's a little bit of a conundrum there. Yeah.
Yeah, that is interesting. So what you're saying is that for the most part, equations don't favor like matter over antimatter. So why is it that we see more matter than antimatter? Why isn't it
Yeah.
balanced? It's
Yeah,
kind of the
exactly.
question that's being
Yeah,
asked.
exactly. And I think similar questions have arisen from, considerations like the arrow of time, like forward in time and backward in time is the equations don't seem to change very much, at least for the most part. So how come forward in time is different from backward in time? So that's sort of the arrow of time problem. And similarly, you say, the equation doesn't seem to favor matter over antimatter that much more. Although with caveat, we'll go into that. There is a slight difference, but it's very tiny. So, but how come we see protons but not antiprotons? Although we do see antiprotons occasionally, right, from cosmic rays, but we just don't have them. Like in our everyday lives, we basically never encounter antiparticles. So what gives? And then to answer this, we kind of have to go over the entire history of the cause of our universe, and then also throw in some physics there and see, is there a solution? Is there maybe something that we missed?
Got it. All right, then let's dig into this. So I guess, Mikey, I'm gonna put you on the spotlight here. What is antimatter? Like what is it? Just we've been mentioning the word.
Yeah, we've been talking about it a lot, but talking about it like it's an obvious thing, but it's weird, right? Like because I can't help but think about, like, it's corny, but like, yin and yang. People have like for a long time, people have appreciated this notion about the fact that in our universe, every concept, observation, it seems to have some kind of an opposite. For every plus, there's a minus. For every up, there's a down. For every positive, there's a negative. And I mean, I guess, so the macroscopic consequences of this were obvious to the ancients. But as a general principle, the fact that our universe necessarily comes with this notion of opposites, it's like baked into the fabric of space-time. As Tim mentioned, that wasn't appreciated until Paul Dirac wrote down the equation for the electron and then noticed, hey, this equation is not complete unless there's an opposite, or what we call a conjugate. As Tim mentioned, this has to do with the mathematical structures that we now know are absolutely crucial for defining particles in motion. This mathematical structure always comes baked in with some notion of a opposite, or sometimes not just one opposite, like like a three-way triplet, or but some notion of like opposition, diametric opposition in some dimension.
I think we should clarify one thing. So this is distinctly different. The notion of antimatter is different from positive and negative, because if you understand quantum physics,
okay.
I just want to clarify, right? Like just having positive and negative does not give you antimatter, because in quantum physics, particles are waves. So you take any particles, which are basically quantum fields. We're another episode covering that in the previously. So a particle is associated with a quantum field, and a field is sort of a wave, and a wave can go up and down, right? So if you just have positive and negative, you don't have antimatter yet. It's the same particle. The notion of antimatter only comes in when you have more than just positive and negative, and you can argue that this is linked to the concept of complex numbers. If you have complex numbers, you don't just have positive and negative. You actually, your number actually spans to a two-dimensional space. You can have extra positive imaginary and negative imaginary, and you can associate the existence of antimatter to the utility of complex numbers in particle physics. The two are sort of synonymous in some ways.
I guess this is a semantic distinction, but I would argue that positive and negative is defined by the act of conjugation. So in my mind, positive and negative is completely dependently tied to the notion of particle antiparticle. But I think reasonable people can disagree about that.
Wait, jargon alert. You guys use the word conjugation. What does that mean?
Yeah, so So I would say so first, if you have one dimensional, a line, you can put 0 in the middle, then positive is the right hand side, and negative is the left hand side, by convention, right? So there's sort of no ambiguity about that. But if your numbers live in 2 dimensions, there are actually multiple ways of doing that now. You can fold this plane in half, then you have the normal positive and negative. We can fold the other way. You can flow horizontally or vertically, right? So there are 2 ways of independent of bisecting your space into 2 halves, right? So the notion of positive and negative, you can think of it as one concept of which side is positive, which one is negative. But then you can do a conjugation. If you look at the other direction, the orthogonal direction, so 1/2 would be kind of the conjugation of the other. The act of conjugation.
Wait, hold on. I want to stop right there. I guess like one point of confusion that I have is, why are we bringing 2 dimensions? Like, what is the point of introducing this like two numbers? Why can't it just simply be like positive and negative? Yeah.
It's a complicated mathematical topic. Can we just say that for all intents and purposes, when we say conjugation, you can think of it as turning plus into minus.
But then why can't you say that with like a proton changing into an electron, for instance? Like what prevents like an electron being like
plus
the
to minus,
anti-proton?
holding everything else constant.
Okay, all right. So I guess because they don't have the same mass.
Yeah.
So what you're essentially saying is like,
I don't know. I feel like it'd be too hard to describe.
Yeah, but I would say that it's not just plus and minus, right? Like certain things you change plus sign to minus, but certain things you hold constant. It's like looking into a mirror. Like if you look in the mirror, your left hand becomes the right hand. Your right hand becomes the left hand.
To be more precise.
But your head doesn't become the foot. Like you don't.
I see.
You only flip some of the signs. You don't flip.
That's a good analogy.
Yeah.
So can I make it as simple as like a particle and antiparticle are an antiparticle and particle pair are 2 particles of the same exact mass but different charge. Like one has a plus charge, one has a minus charge, and that's it. Is that a fair statement? Is there anything more to it? Is my question.
That plus in a mirror, right? Is that right?
Yeah, so I mean, we have another episode covering different types of mirror. I would just say the conjugation is just one particular type of mirror. It flips in the sense of conjugation. I mean, there are different ways of flipping. You can flip in a mirror, you can flip in time, and then
I guess for simplicity, can we just say that it's simply like flipping the charge, keeping everything else constant? It's changing a plus to a minus.
More or less.
Okay. I know they're like, I know there's more subtlety, but just to keep it like really, really simple, can we roll with that? Like
for concept, I think. At the end of the episode, Tim might break that slightly, but
let's go with that, and then later on we can delve into like breaking that notion that it's it's a little bit more nuanced than that. So I guess my next question is, how do we even know that this exists? I mean, Tim, you were talking about Dirac equation, and Paul Dirac, he had this in his theory, but like it's just a theory. So what was kind of the I guess the nail in the coffin, or not nail in the coffin, but the sledgehammer that like proved that antimatter actually exists?
They must have been pretty easy to make once they knew that they were there, right, Tim?
Yeah, and once so I think the first discovery of the positron comes in when they just literally studying cosmic rays. They realize that they have some magnetic fields, and a particle comes in, and for all purposes, it looks like an electron, but it moves, like it curves the other way under magnetic field. So they know that they have an opposite charge. But like Mikey was saying, once you have a particle accelerator powerful enough, you realize that in order for you to produce particles, it tends to be that you have to also produce the antiparticle. Like you can't, like for example, it's rare that you can't just make an electron for nothing. You have to make an electron and an anti-electron. And similarly goes for the proton. Like you can't just make a proton out of thin air. In order for you to make a proton, like even if you have enough energy, it usually comes with an anti-proton, which everything is the same, but it has the opposite charge, right? So, and people realize that, and this pretty much holds for every particle that we've ever seen, even the more complicated ones.
And that's just because of charge conservation. That's just like usually when we crash together, it's like a proton and antiproton, electron, anti-electron. But like in a PP collision, that's not true. Right?
I see. So one other question that I have is like, we've talked about there's an imbalance, but is the imbalance like there's no antimatter and there's all matter, or is it like, is there a ratio of matter to antimatter? Like, how do we think about the imbalance?
Yeah. So I think this becomes a little bit more subtle now. So one has to remember that in the early universe, the whole universe is in a plasma, basically. There are many different particles. And the reason why the imbalance is such an intriguing problem is that when the universe is created, you get matter and antimatter, and it should almost be an equal quantity. But let's imagine we have a universe that's perfectly balanced. Okay, so we have for every unit of matter we have antimatter. Yeah. So the universe is really hot, and as it cools down, it doesn't have enough energy to keep making matter antimatter anymore. Because if you have light that just has enough energy, you can just pop out matter and antimatter pair. But at some point it cools down, there's no more energy now, right? So what will happen is slowly these pairs will annihilate each other. Okay, so when a matter particle finds an antimatter, they will just annihilate in a flash of light. And if that were to happen perfectly, there will be nothing left in the universe, basically. Everything will decay into light. And the universe is empty. So if you trace back to the history of the universe, we realize that at some point, after all the annihilation is said and done, when everything, and when every particle meets an antiparticle, there is a bit of a leftover. And that excess, you have to measure in some unit. Usually it's measured in units of excess number of matter particle divided by the number of photons, which is the reference. And that's 1 in a billion. So it's very, very tiny, right? And it powers our entire universe. Like galaxies, planets, stars. And if it was just a little bit less, we would have a lot fewer galaxies. And if you were just a little more, we have a lot more matter. So kind of like the way our universe is very sensitive to this. It's very sensitive to this tiny excess.
Yeah. So just to reflect back what you were saying is that let me think how to phrase this. So essentially the way to compute like you can think of like a photon as like made up of, in terms of this counting, as like both matter and antimatter. So when they come together, they produce photons. And so the way you're computing this 1 in a billion is like for every matter particle, there are a billion photons in terms of that ratio. Is that correct?
Yeah, roughly speaking.
It's almost like
Okay.
at the very beginning of the universe, you had a billion matter particles, you had a billion antimatter particles, and 1,000,000,001 matter particles. And then they all collided, and you had one left over that made the whole universe.
Yeah.
Oh, wow. So everything that we see in terms of the matter part of our universe is basically that 1 in a billion imbalance.
Yeah.
Okay.
Yeah. Although
that's quite amazing.
Oh, this number is not precise because the number of matter or antimatter particle, it fluctuates, right? If you have more energy, you can make more pair. So, but loosely speaking, 1 in a billion.
Yeah, totally just an analogous thing. And I just wanted to point out, like, this isn't the only time we see this. We've had other episodes about the anthropic principle where it's like there are these little things that are just right, just like maybe if they were exactly the same, we'd get nothing, but it's just a little bit off. So now we have structure. If it was a little bit more, it'd be just be chaos. So So this is one of those things where it's just very curious. It really keeps you up at night thinking about like how this could have somehow arranged itself to be.
Mhm. Yeah, I mean it is interesting. I mean, I guess you're talking about like the fine tuning problem. Is that right, Mikey?
Fine tuning problems.
Yeah.
All
Yeah,
right. Mhm.
I would say this is analogous to many of the physics problems that we have. When a number is so small, like it wouldn't make sense if it was zero. Of course, there will be no universe to live in. But like if it was zero, it'd be like, oh, you know what? The universe is just in perfect harmony. Matter, antimatter exist in the same plane. There's not one is prioritized over the other. It would make sense if it were zero. Right. And if the universe didn't like matter over antimatter, you would say, wow, that if the universe really just prefer matter, there'll be way more matter. It wouldn't be 1 in a billion. It would be like 1 out of 3, something like that. It wouldn't be 1 in a billion. So it's almost like there's got to be something that makes this number so tiny, but yet it's not exactly zero.
Right.
Just like, like, yeah.
Oh boy. Okay, so I guess let's Tim, you had talked about like with some small caveats, tiny like fine print caveats, that for the most part the universe treats matter and antimatter symmetrically. Let's get into the fine print of like where it doesn't treat it symmetrically, if that exists.
Yeah.
It's so silly. Yeah, I just wanted to preface that. It's so silly. Tim, go ahead.
Yeah, and it turns out that it has to do with the weak force, which is responsible for radioactive decay. So I think back in I've got the timing. People have proved that when nuclei decay happens, there is a slight preference for matter over antimatter, or whatever, depends on your convention, right? That it doesn't treat both the same way, and this is a violation of this symmetry. So, for all intended purposes, this mirror, this symmetry is an approximate symmetry. Like the standard model of particle physics doesn't respect it wholly. It just respects it most of the way. It means that in almost all the reaction we see, unless you're really careful with the way you build your experiment, you will not observe it. Like, for example, if you try to make a proton, you kind of have to make the antiproton in equal amounts, right? Only in very, very rare circumstances, you have these really particular decays, do you observe this asymmetry. And if you just do a little bit of calculation, this amount of asymmetry turns out to be just too small. Like, I know like 1 in a billion is small, but like the amount of asymmetry we have in our theory, it's even smaller. So it just couldn't get you that 1 in a billion even.
But it shows that it's possible.
Exactly. Yeah. So it shows that there's no real principle in our universe that says, why matter should be equal. I guess the universe has no democracy in terms of matter, antimatter. It doesn't care.
Wait, can we rewind this experiment though? And Tim, can you support me on this? Because I know you know more about this, but I mean, like you can describe it in a more dramatic way, right? Like essentially the question these physicists were asking in the 70s was, let's imagine a bizarro universe where left was right. Just where left was right. Like the mirror universe. Like, sometimes we imagine we're walking by a mirror and you see the entire universe reflected in the mirror, that maybe that mirror could reflect a different reality. Could you tell if you were living in our universe or if you were living in the mirror universe? And they didn't experiment to test whether or not it was possible to distinguish. And the answer turned out to be yes. And that's the experiment that Tim is describing right now.
Yeah, I think there's a whole slew of experiments. There's the parity violation.
Yeah, that's the one. Yeah, that's the big one though.
Yeah, but there's the more intricate, the C charge conjugation and parity.
Yeah, but the parity one is the one that's the most like, whoa, that's like the most like in your senses. It's like most directly related to your senses.
Yeah.
You can
Yeah.
distinguish the mirrored universe from ours.
And,
Yeah, I don't
and just to
remember.
clarify, Parady's looking in the mirror. They just want to make sure I
Yeah,
relate
yeah.
the two
Yeah.
terms.
Yeah,
Yeah.
it largely has to do with when you take spin into account, because if something is spinning, we're talking about quantum mechanical spin, but the analogy in ordinary physics works. Like if a top is spinning like this, in the mirror, it should like spin opposite, right?
Mhm.
And then if you add that together with the way particles decay and all that and charge conjugation, it turns out that it's not true. Like the spin doesn't flip. It's something like that. It's very complicated. You have to
Very subtle. It's
very
like
subtle.
if you wanted to determine if you were living in the mirror universe, you would have to devise such an overly clever experiment. It's insane.
You have to be very smart.
And
You have to
it's
be very
crazy that
smart.
we were able to do that. I think to me that's like a big point of pride
Yeah.
for particle physics progress. It's crazy.
Yeah. I guess like one question that I have is we mentioned in previous episodes the concept of inflation, like, you know, that in the early
Whoa.
universe it just blew up into like a huge, like unbelievably huge in a very short period of time. What if there was an equal amount of matter and antimatter, but they just blew up so fast that like there's no way they
That's
could like
separated?
interact in time? Yeah, they got separated. So maybe there's another universe that
Yeah.
has like antimatter, that has like antimatter versions of us calling it matter. And
So
I don't know.
that
Wait,
so
Tim, is that possible? That sounds
yeah
that doesn't sound crazy.
that is a plausibility. But we have experiments that constrain some of these scenarios. So imagine it were to happen. You have patches of well first of all, you have to explain why there were these patches of extra matter and then extra antimatter, right?
No, there would be like, Gaussian density,
Exactly.
like, right? Yeah.
Yeah, exactly. If quantum fluctuation will produce a very particular types of statistics. And then when you blow it up, you know, occasionally you'll see these boundaries. There will be boundaries between where the matter frontier is and the antimatter frontier is. And those boundaries will be pretty violent. Like you can have galaxies made of ordinary matter, because for all intended purposes, they are very similar. And then galaxies made of antimatter. And at those boundaries where they collide, boom, you can have a very violent reaction. And we should be able to see these in the sky, and they will be very dramatic. Like imagine, and you can also almost imagine like imagine the universe will be kind of have these patches, and the borders of them will like light up. You see like cracks. It's almost like cracks in our cosmos, kind of, right? These are like like macroscopic. Is it called macroscopic strings, defects, whatever you call it? But we don't observe it. So if it was true, either the patch has to be very, very large, right? But then I think the statistics, it wouldn't be that easy to achieve. You have to, you know, just by random quantum fluctuation, you have to create large enough of a patch that inflated to be such a large extent that we don't see the boundary yet. But that is actually a plausible explanation.
Are you saying it's possible but not generic, Tim?
Yeah, and it depends on like how. I mean, if you play this game and it comes down to the nitty gritty details, right? Like, you know, is our universe likely, given these scenarios, given that we haven't seen the boundaries? But that is a plausible explanation.
Yeah, nice theorizing.
Yeah. Oh, thank you. I may have to give credit to Leonard Susskind. I think he might have proposed this or like some idea, but just I don't know. I just thought like, yeah, go ahead.
Yeah, but usually in your version of the theory, we're going to talk about some of the solutions, right? You probably need a mechanism to generate these large patches of like excess of you know, matter over antimatter.
Mm-hmm. Got it. So I guess Tim and Mikey, where does this leave us? Yeah, maybe you can delve into some of the solutions that people have like come up with.
Yeah.
So So of course you can argue that this is just silly, like doesn't mean anything, right? But I think when you do science, well, I'm just saying. Of course, you can always
That's
argue.
silly.
You can always argue some physical problems is a non-problem, right? But that's not the spirit of doing science. The view is that this is like it's a hint. It's a hint that nature gives us, and maybe it's pointing to something else. I think many interesting theories occur when you combine this fact with another mystery, right? So some of the most leading hypotheses to explain the excess of matter, antimatter, comes from when you combine this problem with another one. Yeah. For example, if you believe that maybe there's some, if the universe has an enhanced symmetry, you can combine it with supersymmetry, and you might think that.
Wait, for symmetry. Dragon alert. I got you, Sahil.
Yeah, I mean, I'll refer the audience to one of our episodes on symmetries, right? Yeah. So
dodge that one.
If you like symmetry, you can provide solutions in the realms of supersymmetry. Or if you like, let's say, you think dark matter is a mystery, you can combine dark matter and the asymmetry, this matter asymmetry of the universe, and come up with what we call asymmetric dark matter. These are pretty popular models a few years back. And then there are also some more like brute force explanation. You just say, hey, there's some physics that we're missing, and it can just brute force create excess matter.
Well, we know what the minimal requirements are to do this, and then you can kind of parameterize like a skeleton model that can do that without, and use it to try to make statements about other things.
Yeah.
Wait, so Tim, real quick, on the asymmetric dark matter, asymmetric dark matter that you were mentioning. Would that even be feasible? Because like if I take the definition of antiparticles where it's like, say, the opposite charge in some sense, it still need to interact with light. Would these be like neutral or like what? Yeah, just what would that be about?
Yeah, I mean, you have to fix the model. I mean, then you have to add some preference to matter, and somehow dark matter have some preference to antimatter, and that's how you. That's how you. Basically, the whole concept is that the matter we see is the matter we see, but the antimatter that we don't see is actually hidden in dark matter. Somehow it got pushed to dark matter, and you have to inject this asymmetry. Somehow the universe prefers matter for the ordinary matter form, but dark matter is preferred in the antimatter form. Of course, which one is matter, which one is antimatter is by convention, but like you can arrange that to happen, right? So that's one solution. I mean, we can go into more details. But the other solution also will have to involve some preference, whether it's embedded in the theory or artificially generated from dynamics, basically, like things that happen.
Don't say artificially. That makes it sound.
I see. I guess there was something you were mentioning also about like protons and antiprotons as well. Do you want to bring that up, or is that a separate discussion? Like baryonic number and whatnot.
Yeah.
Snap.
Well,
I feel like you're doing so well without the jargon.
Yeah.
Okay, we don't have to bring it up then.
No. I think.
Let's bring it. Yeah, do it.
I think it's worth a mention, right? So basically, if you think, this is trivial, I can just add something in the theory and just make it happen, right? It's not as simple as you think, and the reason is because this approximate equality between matter and antimatter helps our universe. It ensures that the ordinary stuff doesn't just disappear, right? And one of the laws that help protects this is what we call baryon number conservation, right? What that means is, if you count proton and neutron as having baryon number +1, and antiprotons. Actually, a neutron is it's. I'm a little stuck. Yeah, but okay, but anyway, yeah. If you count protons as having positive baryon number, and antiprotons have negative baryon numbers, you see that whenever I try to create a proton, I always have to offset it by an antiproton, right? It also means that when that's approximately true, it means that a proton can't just disappear, you know. So if you just add something to your theory that says, oh, I can just create a proton out of thin air without creating antiprotons, what ends up happening is that you might accidentally cause the proton to decay. And that would be terrible because we have experiments that shows that protons really don't decay. You know, we have massive vats of substance to wait for proton decay, and we've never seen it happening. So proton, for all we know, is very, very damn stable, right? So basically, you can try to violate this baryon number conservation, but if you do it in a non-clever way, then the universe will decay away, and that's not good.
Oh, that definitely is not good. I want to propose another idea. I don't know how valid it is, but around the concept of like symmetry breaking, for my own amusement. So I remember early in the universe, if you really believe that there's like one object, it's like the most symmetrical thing, and as the universe cooled, it essentially cooled into like, it broke certain symmetries, and so the universe is less symmetrical than it was when it was like really, really hot and dense, for instance. So could you make the argument that maybe matter might be a like specific configuration of this object that has its symmetry broken, and that it happened to just be that direction? Like, if I think like of a pencil on top of like a hill, and the wind just happens to blow it and it just falls in like a particular direction, but it could have very well chosen any other direction.
Yeah, so that is one class of theories that propose the solution. So your proposal is reasonable, and this is very similar to what we call the Higgs mechanism. So the Higgs field is what gives rise to masses for some of the particles, and the idea is that the Higgs field, because it's what we call a scalar, it has no feature, it's a featureless thing. It's able to pick up a value, so it can just point into one direction, and that makes the weak force different from the electromagnetism, right? So if you were to propose a similar thing for baryon, to somehow say, hey, baryon is different from anti-baryon, you need something that's featureless, that's able to pick up a value, so that the universe favors baryon over baryon. And you can't do that with quarks or protons and neutrons, because quarks has features, and quarks themselves cannot say, oh, you know what, we're just going to pick up a quark value. You can't do that, because that will actually destroy other symmetries of the universe, right? So your proposal is plausible, but we need what we call something like the Higgs field, but for baryon number, right? So you need to engineer that, and people have, and it turns out that if you add supersymmetry to your theory, naturally that happens, right? Because in the previous episode we talked about supersymmetry, because when the matter particles, quarks, will now come with partners, the squarks, the scalar quarks, and and this is exactly what we're looking for. It's a scalar field that, like the Higgs field, that can pick up a value. And these are some of the most popular models back in the days when people had hopes that supersymmetry might be found. And that's that used to be one of the leading contenders for solving the matter over antimatter problem, I think.
Yeah. Okay, so I see. So basically, you would need to create another object that would give rise to that symmetry breaking, essentially, is what you're
Yeah,
saying.
yeah, exactly. And pretty much like all the solutions will require us to find something new. Like basically like a driver for an asymmetry toward matter over antimatter.
Got it. So,
if you will.
what did you say, Mikey?
I said a fly in the ointment, if you will. That's a saying, right?
I've never heard that saying before until now.
What? Google it. It's a popular saying.
Wait, what? I don't.
A minor irritation that spoils the success or enjoyment of something.
I mean, I've heard of ants at a picnic. That's
fly in the ointment.
Okay, so we have an audience question, which is a little bit more technical, but can the violation on Lorentz invariance lead to CPT invariance and consequently to matter antimatter asymmetry? Maybe we can break down that question, what it means.
Well, sorry, continue.
I was saying maybe we can like break down what the question is asking in more layperson terms and then answer the question.
Yeah, violation of Lorentz invariance means
we'll destroy everything. Nothing will make sense.
It means the violation of Einstein's relativity. Yeah. And also there's this thing called the CPT invariance. I won't go into details, but it's a mathematical proof that any sensible theory, if it obeys Einstein's theory, should have this extra symmetry, which combines.
No, the point is though, if you don't have Lorentz invariance, you can't even define CPT. What is CPT?
Well, basically, I think it's trying to say that CPT is gone. If you don't have Lorentz invariance, CPT is gone.
You can't even define what CPT means if you don't have Lorentz invariance.
No, you could. There just isn't CPT invariance, basically. Yeah.
Well, okay, so if we just have a Euclidean space, I guess you could define parity. Then what's the difference between parity and time reversal?
I mean, you could define it, but it's not invariant. But I think the crux is Lorentz invariance, at least from experiments, the violation, even if it exists, is so small. It's way smaller than 1 in a billion. So even if something like that were to exist, there's no way it can generate the type of antimatter asymmetry we observed without also contradicting some of the other experiments. So
if Lorentz invariance is violated, then someone has to explain to me how spin exists.
Yeah, exactly. Yeah. So
so basically, just to translate this question, what it's asking is if a special symmetry from Einstein's relativity is broken, then the symmetry of if you were to take the universe, put it in a mirror, change all the particles to antiparticles, and have time going backwards, that symmetry would no longer be there.
It's no longer guaranteed. It can still be there, but it's not guaranteed. It's not mathematically guaranteed. But
I would argue that you can't even define unless you tell me how the Lorentz invariance is broken. I can't even tell you what the difference is between parity and time reversal because you haven't told me what. If it's a Euclidean space, then P and T are the same thing.
You mean Euclidean meaning like a flat space, like just...
Yeah. Like if it didn't have a Lorentzian signature, if there's no Lorentzian signature, or if Lorentz symmetry is violated in some small way, then then I guess you could still define approximate notions of C, P, and T.
Yeah, but in any case, it's almost like the end doesn't justify the mean. Like it's so much violence if you break if you break Einstein's relativity, there's so much more you need to explain. And let's say for some reason you're able to explain the matter-antimatter asymmetry, but you just open an entire can of worms. Basically the explanation is not worth it.
One problem and making a million more.
Yeah, like you solve one problem, but you generated a few million more. Like it's just not worth it. It's just not economical. I would say.
Yeah, I have to say, this is an uncharacteristically strong reaction for me, and it's because of the fact, as Tim noted, that there's definitely a bias in the physics community to not question Lorentz invariance or the theory of special relativity. It's just so hard. And if you think you can do it, okay, you're the man.
Yeah.
Okay.
But quartz it's way less than 1 in a billion, at least number wise. Like
no, you can't even put a probability to it. It's just like, it's almost delusional if you understand how deep it is in the pillars of so many other things that we know to be true.
No, I would say if you break it, the effects won't be as large as you think because of other experiments. Basically, it will definitely be.
You mean it can't be as large as you think?
Yeah, it just cannot be 1 in a billion. Maybe 1 in like a trillion, something ridiculously small.
Yeah, no, there's not enough time to keep saying the number of trillions.
Okay, so we have another audience question, which is I guess kind of piggybacking off what you mentioned, Mikey. So I'm going to actually point this question to you. How is spin defined in terms of Lorentz invariance?
Spin statistics theorem. Okay, I'm not going to pretend I understand it. Like, it's a very, 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 very long, complex mathematical proof. But the discretization of spin is very much tied to the structure of Lorentz invariant spacetime in 3+1 dimensions. There's a very good book I can refer you to if you want to see the direct proof, but it's our understanding of why particles have spin is deeply tied to the robustness of Lorentz invariance.
Yeah. Basically, spin statistics theorem tells you to go into the technical stuff, but don't worry if you don't understand the lingo. It tells you that fermions and bosons, fermions have to have integer spin, and bosons have to have integer spin. This sacred connection it can be proven mathematically if you assume Lorentz invariance. If you destroy it, it's gone. That link is gone. So it's like, well, all hell's break loose now. Like a scalar, can be a fermion now. The connection is just broken. Now you have way more explaining to do, basically. And so that's another one of the reasons why it's not you don't mess with Einstein's relativity. You just don't.
It gave us so much. If you attack it, it'll take away all that it is.
It'll take away all the good stuff you treasure in the universe. So don't do that. It's like it's not worth it.
Yeah. Well, I'll tell you, I won't be taking it away anytime soon. So we're almost at time. So I wanted to give you guys a chance to, our tradition, leave the audience with any, words of wisdom that matter and antimatter have taught you, or rather the asymmetry.
I'll be real quick. I just think this is just another beautiful example of, among so many other examples that we've talked about, of how like a perfect balance creates chaos, and too much imbalance also creates chaos. But what we need to thrive is just a little tiny little fly in the ointment, so to speak.
Yeah, and I would kind of follow that theme, right? Like, we've seen time and time again in the realms of fundamental physics, to have an interesting world, you need symmetries that are beautiful, that makes things simple, but not too simple. You need this little bit of offness, just a little off, perfect balance, to create like an almost very structured universe, but not like total chaos. Like, for example, if you imagine with a little too much matter, the universe might have collapsed. It might have expanded not fast enough. It might have formed a lot of black holes, and with none of these beautifully intricate structure. So even though it seems like so, I guess for those of you who are the audience who are not maybe familiar with the way fundamental physics work, it's like, oh, there's just some number 1 in a billion. Who cares, right? But like, there's so many of these numbers in particle physics where if it's just a little off, the whole thing falls apart. These in my mind, these are like the hints that nature is dropping us. It's like maybe that number by itself doesn't mean very much, but certainly there should be a reason for that number. It's not just any accident. Yeah, and I think if we find the ultimate answer in one of these days, all these small numbers hopefully will eventually be explained.
Yeah, I'm hoping, although probably not sure if it'll be done in my lifetime. Yeah, so well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
All right, see you all. Bye.
Bye.
Bye.